Hey everyone, welcome back to my channel. In this video, I'm going to go over Euclid's algorithm, which is a really efficient algorithm for finding the greatest common divisor between two integers. We're going to look at the algorithm, we're going to see an example of it, and then we're going to go into a coding example where we're going to code out Euclid's algorithm using Python. So let's get started. So let's start by reviewing the greatest common divisor of two integers. So the greatest common divisor, we often write it as GCD, and in this case I have two integers, m and n, is the greatest integer, that's why I have max, and I'm going to call this integer k, such that k divides m and k divides n. So let's look at an example. Let's say I'm looking at the greatest common divisor of 12 and 18. So these have a few shared common divisors. So for example, they're both even numbers. So I know 2 divides 12 and 2 divides 18. But if I want to find the greatest integer that divides both 12 and 18, since they're not incredibly large numbers, I know right off the bat that this is just going to be 6. 6 goes into 12 twice, and 6 goes into 18 3 times. So it's pretty straightforward when we have relatively small numbers, but this becomes really complicated and a really expensive operation once we have really, really large integers, and that's where we're going to get into Euclid's algorithm. Euclid's algorithm consists of the following recurrence relation. We have our base case, which states that the greatest common divisor between 0 and n is equal to n. And I think that's pretty straightforward to demonstrate, but just so that we can see an example of it, let's say that I want to find the greatest common divisor between 0 and 12. So any integer can divide 0. I can have 0 over 1, I can have 0 over 2, and so on. And then for any integer, the greatest integer that divides that is the integer itself. So if I'm looking for all integers that divide 12, the greatest integer that divides 12 is actually going to be 12 itself. You're always going to get 1. So anytime you're looking for the greatest common divisor between 0 and some other integer, some other positive integer, it's going to be the positive integer. In this case, it's going to be 12. So that's just an example. Okay, now for the second portion, as an example, let's say that I have 0 less than or equal to m and less than n. And I'm just assuming that this holds, but when we go into the coding portion, you're actually going to see that there's a self-correcting mechanism in Euclid's algorithm to where you could switch the order of m and n and it'll still work. But for now, let's assume we have m less than n. So we can, using the division algorithm, we can write the following relationship between m and n. I can say that n is equal to m times the floor function of n over m plus n modulo m. And now what the floor function is like, just as an example, let's say that I have 18 over 12. If I actually divide that, if I want to use a decimal, I would have 1.5. But if I were to take the floor of that, so floor of 18 over 12, I would just have 1. So that's the floor function. Also, if this looks a little abstract, a lot of times you can actually see it written with different notations. Usually this floor function is just going to be called the quotient, and n modulo m is just going to be called the remainder after you divide n by m. But we can actually rewrite this, and I can rewrite this as n modulo m, which is equal to n minus m, and for simplicity I'm just going to rewrite this as the quotient. I think that's easier to read. Now the reason this holds is, let's assume that we're looking for the greatest common divisor. So we're looking for a number that divides m and n. So here, let's say we have some number. If k divides n and k divides m, as a property of divisibility, I know that k is also going to divide n minus m times q. and we're just multiplying by a quotient, so that's another property of divisibility. So we know that k is going to divide n minus m times q, and since that equals n modulo m, I know that k is also going to divide n modulo m. And that proof is just going one way. You can do the proof going the other way, where you start with k dividing n modulo m, and then you can show that k also divides n minus m times q. Okay, now that we understand the recurrence relation, let's look at an example, and let's use some relatively small numbers just so that it's easier to understand. When we get into the Python coding portion of this, we'll look at some larger numbers, but let's start with, we are looking for the greatest common divisor of 12 and 18. I can see that I haven't reached my base case yet, so I'm going to use the second relation, and I can rewrite this as the greatest common divisor of 18 mod 12 and 12. And you can see I'm just using the second relation right here. And I can actually solve for 18 mod 12, so I can rewrite that as the greatest common divisor of 6 and 12. And I haven't reached my base case yet, so I can keep this going. I can rewrite this as the greatest common divisor of 12 mod 6 and 6. I'm going to solve for 12 mod 6. And that's going to give me the greatest common divisor of 0 and 6. And that's because when I divide 12 by 6, 6 goes into 12 twice evenly, no remainders. So I have 12 mod 6 is 0. So I have my GCD of 0 and 6. And you can see right here, we've already reached our base case. And then if we follow this property from our base case, we know that this is just going to give us 6. So using Euclid's algorithm, I've shown that the greatest common divisor of 12 and 18 is equal to 6. This is a very long-winded way of solving the greatest common divisor for small integers, but let's jump into the Python coding portion of this, and we're going to see how this is really, really useful when we work with larger values. Now let's code out Euclid's algorithm using Python. I'm going to try to make the code look as close as possible to the math that we were looking at earlier on the whiteboard. So let's go ahead and define a function. I'll say def Euclid's algorithm. We're going to take two parameters, m and n. And first we're going to do our base case. So if m is equal to 0, return n. And that's that condition we were looking at earlier, where if we had GCD of 0 and n, we return n. So that's the base case. And else, I'm going to actually print out several statements here just to kind of help us see what's going on. This is going to be really useful if we enter larger numbers. So first off, I'm going to have an f string just to say that I'm calculating the GCD of an m and n. And that's going to show me where I'm at each iteration. Then I'm going to say print, do another f string, and I want to see my remainder. I want to see n modulo m, so I'm just going to do n mod m, and I'm actually going to show what it is. So let's just do n mod m like that, and then I want to see what the result is of that division algorithm, or what the division algorithm is at that step. So I'm going to say n equals, and let's do m times the floor function of n over m, which is going to be n / m. That'll give us our floor function, and then plus our remainder, which is just n mod m. Okay, let's see. So yeah, n is equal to m times the floor function, or the quotient, plus the remainder, n modulo m. All right, and then finally, I'll call the function again, so return Euclid's algorithm, and I'm just going to pass in n mod m and m. Okay, and now let me go ahead and create an entry point. So if underscore underscore name equals main, I'm going to get input from the user. So I'm going to declare one variable, m is equal to, it's an integer input. and I'm just going to say enter the first number m, and I'm going to do the same thing. I'm just going to say n is equal to int input, enter the second number n. Okay, and I'm going to assign that to a variable called GCD, and I'm just going to get that from calling the algorithm, passing in m and n as my arguments at that point, and I'm just going to print the result. So I'm just going to say, with an f string, the greatest common divisor of m and n is, we'll just show the variable we assigned GCD. All right, there we go. We save that. And let's go ahead and try to run this with a couple examples from the terminal. So let's say python-m, we'll call euclid.alg. Okay, enter the first number. Let's try the example we're looking at, 12. Enter the second number, 18. So that calculated really quickly, and that was really neat because it showed us exactly what we saw when we were working this out on the whiteboard. But now, one thing I was mentioning earlier is we can actually flip the order where m, basically the m is, it's possible to have that larger than n. So here's what that would look like. Let's call this again, and now let's do 18 and 12. We flip the order. We get the exact same result. But what you notice here is there's actually an extra step, because what happens is at the very beginning, we're actually calling, originally we were calling 18 modulo 12. So we were doing 18 divided by 12 and getting the remainder of that. But now here, for the first step, we're calling 12 modulo 18, which is 12 divided by 18, getting the remainder of that, which is the quotient is 0. We just have a remainder of 12. And now we're actually passing that in because that remainder becomes the first value in the next step. And our original m, we're moving that over into the second value. So what we get is after the first step, it actually corrects itself. And the rest of the algorithm is exactly the same as if we were to have the first number smaller than the larger number. So that works for larger numbers too. Let's just kind of check it out. Let's try 2, 4, 5, and 7, 6, 0. Okay, I knew that one was going to be 5. 2, 4, 5, and 7, 6, 0. And let's try that again as 7, 6, 0, and it was 2, 4, 5. Yes, and 2, 4, 5. All right, and we get the same thing. Obviously, it was going to be 5, but it's the same thing because we can kind of see that after the second step in our algorithm, it actually does what we were doing in the very first step had we put the first number in being less than the second number. All right, so that's kind of an interesting fact. And also, I was talking about why, it seems like it's so much longer to do it this way, but let's put in some really large numbers. Let's try, and I'm just making these up on the fly. That seems like a big number, and that seems like a much bigger number. There we go. Oh, I didn't even call it. Let me call it. There we go. So let me first try this number. And then let me do the second number. Copy. Okay, so this actually looks like a lot because there are a lot of outputs in here, but relatively given the size of this number and just the size of these two numbers, this really isn't that many steps. And if you'd like to see a future video, just let me know in the comments. I'd love to do another video explaining the time complexity of this. But please let me know if this video helped, if you have any questions, suggestions, ways I could have made this better. But I just want to say thank you so much for watching, and I'll see you next time. Take care.